Hello everyone, here's my second video for notes for my Unit 1 Notes Part 3. So moving on, we're going to start to calculate empirical formulas. So just as a reminder, an empirical formula is defined as the simplest or most reduced whole number ratio of the atoms in a compound. So sometimes scientists, chemists in practice have unknown substances that they have to analyze, right? And they might do a combustion analysis, burn that substance to see how much CO2 and H2O comes out of it in that combustion reaction. They might run it through a mass spec. They might do gravitational analysis. They might do any number of things to analyze some sort of unknown samples. And a lot of times, they'll actually end up getting some form of data that they can use to then identify that substance. And one way to go about doing that is calculating an empirical formula so that you can then extrapolate it, do a couple of other calculations to figure out what the molecular formula of that compound is and actually identify it. We're not going to do all of that today. Instead, we're going to take some data and use that to calculate empirical formula and then use a known molecular molar mass to then figure out that molecular formula. Okay, so on the left here, you see a set of 4 different steps. And those steps are going to tell you what to do when you are asked to calculate empirical and molecular formula based on the types of problems that you will see in this class / on the AP test. So, looking at our first practice problem, let's figure out what it wants us to do. It says, what is the empirical formula for lactic acid if, by analysis, it is found to contain 40.0% carbon, 6.71% hydrogen, and 52.9% oxygen by mass. So again, we're trying to figure out the empirical formula. Somebody did some sort of analysis and we got those percent by mass data pieces. So, step 1 says, convert starting amount, grams or percent, into moles using their molar mass. And this little bullet point A says, if the amount is given in percent, assume that you have 100 grams of that substance if no gram amount is given. And the reason that we are going to do that, we're going to take these percents and assume that we have 100 grams of that substance, is just to make our own lives easier. Because if I have 100 grams of a substance and 40% of it is carbon, then I have 40 grams of carbon. And if I have 100 grams of a substance and 6.71% is hydrogen, then I have 6.71 grams of hydrogen. So I didn't need to do any extra math by making that assumption. So I'm just going to put grams here, just so that we know we are assuming 100 grams of the substance so that these percents cleanly will change into a gram amount. And then we're going to follow step 1. We are going to convert that amount to moles using the molar mass of those substances. So we know we need to find that on the periodic table. So I'm just going to go ahead and do that. We're starting with 40.0 grams of carbon. I know on the periodic table that 1 mole of carbon weighs 12.01 grams. I plug that into a calculator and I get 3.33 moles of carbon. Switch colors, 6.71 grams of hydrogen. On the periodic table, 1 mole of hydrogen weighs 1.008 grams. Therefore, I have roughly 6.66 moles of hydrogen. Starting with 52.9 grams of oxygen. On the periodic table, 1 mole of oxygen weighs 16 grams, which means I have roughly 3.31 moles of oxygen. Okay, so that is step 1 done. Check. Step 2 is to divide all of our mole values by the smallest of all of those moles. So, to do that, I'd identify the smallest one. If I look through my list of 3 here, 3.31 is my smallest, so what I'm going to do is divide everything else by 3.31. So I'll draw a line and we'll just do that real quick. I have my 3.33 moles of carbon, and I'm going to divide that by my smaller one, 3.31, and that is going to give me 1.01. I have my 6.66 moles of hydrogen, dividing that by 3.31 again, and that's going to give me 2.01. And then finally, I have my 3.31, which I'm going to divide by itself. And that is going to give me 1. All right, so why did I do that? Why is that necessary? Because this step essentially standardizes your mole amounts relative to each other. And it's going to give us that whole number ratio of 1 to the next, just like an empirical formula needs. We want that whole number ratio. Okay? Now, I'm going to follow step 3, and I'm going to round to the nearest whole number if my decimal value is less than 0.2. Otherwise, we're going to end up having to follow step 4. So let's look at my decimal values here. I have decimal values of 0.01, 0.01, and 0.00. All of those are less than 0.2, so I am safe to just round those off to whole numbers. So that 1.01 is going to round to 1, 2.01 is going to round off to 2, and obviously 1.00, you don't even need to round it, it is 1. So that tells me that I have 1 carbon, 2 hydrogens, and 1 oxygen in my empirical formula. That is my whole number ratio. So your answer is going to be C1H2O1. Okay? If I had some weirder values, if I had like 1.25 here or something instead, then I would have had to follow step 4 and multiply every single one of those values by 4 to get my whole number ratio. But we'll address that in a little bit when we do the challenge problem. Okay, so that is my empirical formula. I can use this information that I figured out here to calculate a molecular formula, right? So that's my next practice problem. I can use that to figure out molecular. My next problem states, what is the molecular formula for lactic acid? And it gives me its molar mass. If, by analysis, it is found to contain 40% carbon, 6.71% hydrogen, and 52.9% oxygen. So again, that's the same data I have up here. Because this is just effectively part 2 of that problem, I don't have to do all of this again. I already did it in part 1. So I'm going to use my answer from part 1 to do part 2. For a molecular formula, we need to figure out its multiple n. So what's that factor that we can use to scale up the empirical formula to the molecular formula? And we can do that by dividing the molar mass of the actual molecule, which is that number in the problem, by the molar mass of the empirical formula, which I just figured out, right? So all I have to do is figure out that molar mass of my empirical formula and divide this number by it. Okay, my empirical formula has 1 carbon, which is going to be 12.01. I have 2 hydrogens, which is going to be 2 times 1.008. And I have 1 oxygen in it, which is just 16. I add all of those up together, and I get my empirical formula's molar mass, which is 30.026 grams per mole. So, according to my formula over here, all I have to do is divide the molar mass of the molecular formula by the empirical. So, I get N equals 90.08 grams per mole on the top, divided by my molar mass that I just figured out of my empirical formula, 30.02 grams per mole. And I get 3.0001. I am going to round that off to a whole number, 3. So that 3 is my multiple that tells me how many I need to multiply my empirical formula by. So just as a reminder, my empirical formula is up here, C1H2O1. If I multiply all of those subscripts by 3, I get that my molecular formula is equal to C3H6O3. And that is my final answer for molecular formula. Okay, I know it's a little bit confusing, and you're probably wondering, again, why go through all of this? We already knew the molecular formula's molar mass. It seems pointless, but remember, this isn't the entire picture of what scientists, chemists do in the actual lab. We're doing a small piece of it to learn that process. They, in fact, would have to do a lot more analysis and some calculations to figure out what that molar mass is, and then they could do this process to figure out a molecular formula. Okay, now we're going to move on to the challenge problem. The challenge problem is a little bit intense, I'm not going to lie to you, but it's another form of analysis that you could find an actual scientist doing in a lab. So I just want you to realize, if this confuses you, this is meant to be a challenge. All right, so let's read the problem and let's figure out what we have to do. Our problem states, find the molecular formula when a 1.000 gram sample of vitamin C with a molar mass of 176.12 grams per mole is combusted. The following data is obtained. So first of all, this is a general combustion formula. Those of you who took regular chem will recognize it. The mass of carbon dioxide in the absorber before combustion was 83.85 grams. The mass of carbon dioxide in the absorber after that combustion was 85.35 grams. So basically what that's telling you with its mass difference is that if we subtract those values, we can find out the mass of carbon dioxide that came from that reaction. So if we subtract 83.85 from 85.35, we get that there is 1.5 grams of CO2 that formed in that reaction. Okay? We get a similar data piece for water. Our mass of water in the absorber before combustion is 37.55 grams. Our mass of water in the absorber after combustion is 37.96 grams. So again, if we subtract those values, we can get the amount of water from that reaction, which is 0.41 grams of water that formed in that reaction. Okay, so before we do anything else, I just want to talk about those two values really quickly. We know, based on the reaction up here, that the only two products are carbon dioxide and water. We already know that because of the law of conservation of mass, matter can neither be created nor destroyed, only rearranged. So what we know is that all of this stuff on this side turned into the stuff on that side. And it's very helpful that that's the case, because we can use those two pieces of information about carbon dioxide and water to figure out exactly how much carbon we started with and exactly how much hydrogen we started with. And then we'll just have to extrapolate a little bit from oxygen, because we see that oxygen is actually in two places in that reaction. So, once again, the goal of this problem is to find the molecular formula, which means that I'm going to have to do empirical formula first and then molecular after that. But I'm not given percents like we saw in the other practice problem for empirical formula, so I'm going to have to do a little bit of work to get to some gram amounts that I can convert into moles. So that's what this first step is. How many grams of carbon and hydrogen do I have? So that's the goal of what I'm about to do here. How many grams am I starting with, so that then I can follow this procedure over here? So I know the only data I have so far is carbon dioxide and water. since that's all that I have, that's what I'm going to start with. So I'm going to start with my 1.5 of carbon dioxide and go from there. What I'm going to do is I'm going to use this carbon dioxide amount to figure out carbon specifically. So I'm going to convert my grams of carbon dioxide into moles of carbon dioxide, and then I'm going to use some molar equivalencies found within this compound to figure out carbon. So just go with me here. I can figure out, using the periodic table, that 1 mole of CO2 weighs 44.01 grams, and that is going to convert me into moles of carbon dioxide. What I also know about carbon dioxide is that there is 1 mole of carbon in every mole of carbon dioxide because there's only 1 carbon in that molecule. So really, by converting my 1.50 grams of carbon dioxide into moles of it, I am also going to end up converting into moles of carbon, because for every 1 mole of carbon dioxide, there is 1 mole of carbon that comes out of that. Then, now that I know that moles of CO2 is going to be equivalent to moles of carbon, I can just convert into grams of carbon like I need to do my problem. Because I know that 1 mole of carbon weighs 12.01 grams. All right? So if I do that math all the way through, I get 0.409 grams of carbon. And again, I know that was a little bit tricky to think your way through, but just go with me because I'm going to do the same exact thing for water. I know that I have 0.41 grams of water. All right? All I can do is convert that into moles at this point because literally all the information that I have. I know that 1 mole of water weighs 18.016 grams. All right? In every water molecule, H2O, there are 2 hydrogens. So I know that for every 1 mole of water, there are 2 moles of hydrogen. Remember how I said in the last video that that would become important later? Here's where it's important. Understanding our molar equivalents within our compounds. All right? I also know, based on the periodic table, that 1 mole of hydrogen weighs 1.008 grams. So I have carried myself through my dimensional analysis from grams of water into grams of hydrogen, which is really what I need. And I'm going to find that that is 0.0459 grams of hydrogen. All right? All right. That's working our way to step 1. I have figured out that my vitamin C, my 1 gram sample of vitamin C, started with 0.409 grams of carbon and 0.0459 grams of hydrogen. I haven't yet figured out oxygen, but we know that both of these values, despite the fact that we calculated them from carbon dioxide and water, because of the law of conservation of mass, we know that those 2 amounts of carbon and hydrogen came from my 1 gram sample of vitamin C. And since I know 2 out of the 3 atoms that make up vitamin C now, I can use simple subtraction to figure out the other one. I can take 1.000 grams of vitamin C. I can subtract out my 0.409 grams of carbon and subtract out my 0.0459 grams of hydrogen, and that is going to give me grams of oxygen, which is 0.545 grams. Okay, now that I have done all of those things, now that I've done all of that work, I'm finally actually able to do step 1 of my empirical formula. All right, and I know it seems like a lot, because it is. All right. Now we use our empirical formula steps. Step 1 states that I need to convert my starting amount, in this case grams, to moles. So I'm going to go 0.409 grams of carbon. I'm going to convert it to moles. And that is going to give me 0.034 moles of carbon. I'm going to take my grams of hydrogen, 0.0459 grams of hydrogen, convert that to moles, and I get 0.0455. Last but not least, I take my grams of oxygen, 0.545 grams of oxygen, and convert that to moles. And I get 0.034 moles of oxygen. All right, that's step 1 done, out of the way. Now I need to divide by my lowest amount of moles. In this case, we have 2 that are the same, right? I have 0.034 twice. And so I'm just going to divide all of these by 0.034. And I'm going to get 1.00, 1.33, and 1.00. All right, so now I try to do step 3 up here. I try to round to the nearest whole number if my decimal values are less than 0.2, but they're not. 0.33 is greater than 0.2, so instead of rule 3, I'm going to go straight to rule 4, and I'm going to multiply all of those values by 3. Why am I going to multiply them by 3? Because I had 1.33, and so that's what my rule says to do. So I'm going to multiply all of these by 3, and I end up with 3, 4, and 3 as my whole number ratios, which means that after all of this, I finally calculated my empirical formula. My empirical formula is equal to C3H4O3, because again, these values here are my whole number ratios for that empirical formula. Now that I've done that, I can finally use that information in the problem up at the top, this value right here, to calculate my molecular formula. I know that N, that number, that factor that I'm going to multiply my empirical formula by, is equal to my molecular formula's molar mass, given in the problem as 176.12 grams per mole. And that's going to be divided by the molar mass of my empirical formula. Now for time, I'm just going to let you work that out on your own if you want to pause it, but it is 88.062 grams per mole. I divide those two out and I get 1.99, which I'm going to round off to 2. Then I end up multiplying my empirical formula by that factor of 2, and I get that my molecular formula is equal to C6H8O6. And that is my final answer. Again, this problem is rough. It is difficult. That is why it is the challenge problem. So I don't want you to freak out right now if you're like, I would never have been able to figure that out. I know. That's okay. That's why I'm walking you through it, and we're going to practice with this. So if you have questions about that problem, I'm happy to walk you through it in class when I come back on Tuesday.